we studied the integrals of some standard functions and methods of integrations, etc. earlier. Now, we are going to learn about the applications of integrals. Before that, let us we know some integration. What is a integration? So, already you studied that integration is anti-differentiation of the function, and the integral of a function y is equal to f of x, the integration of any function y is equal to f of x is defined on the domain of f, then that integration is called indefinite integration. Suppose the integration of f of y is equal to f of x is defined on an interval a to b, which is subset of the domain of f, is called definite integration. Already you studied this indefinite integration and definite integration earlier. Now, what is the definite integration? It is the defined on the interval a to b, which is subset of the domain of f. And the definite integration of the function y is equal to f of x is defined as integral a to b f of x dx is equal to f of b minus f of a, where f of x is the integration of the function f of x with dx. Now, find the indefinite integration of the function and substitute the upper limit and lower limit, and difference of the upper limit to lower limit gives the definite integration of the function. And already you studied the methods also, how to find the integration in different methods. That is already over. Now we are going to learn about applications of these integrations. The major application of the integrations is finding areas of the region bounded by the curves. Now let us take some function y is equal to f of x. Now suppose the function is, the graph of the function is like this, and what is the area of the region bounded by this curve y is equal to f of x with x-axis, and between the lines x is equal to a and x is equal to b. Now this is the area bounded by this curve between x-axis and the lines x is equal to a and x is equal to b. Similarly, suppose if another function x is equal to f of y given like this, suppose the graph is like this. Now the area of the region bounded by this curve x is equal to f of y with y-axis and bounded by the lines y is equal to c and y is equal to d. Now this area, now it can be determined by using the integrations. Now this area of the region y is equal to area of the region bounded by y is equal to f of x with respect x-axis, or area of the region bounded by the curve x is equal to f of y with respect to y-axis, or partly some of the portion is above the x-axis and some of the portion below the x-axis, then finding the areas of the curves, areas of the regions formed by the curves, etc., etc. All these areas can be determined by the definite integration. So that the major application of the integrations is finding the areas. Now let us find how to find the areas of these curves. Now let us find the area of the region bounded by some curve y is equal to f of x axis, and between the lines x is equal to a and x is equal to b. Now let us take the function or the curve y is equal to f of x like this as shown in figure, just above the x axis like this. Let it be the function or a curve y is equal to f of x and x is equal to a parallel to the y axis, and x is equal to b, it is another line parallel to the y axis. Now we are going to find the area of the region bounded by this curve y is equal to f of x with x axis and the lines x is equal to a and x is equal to b. So this part. Now to determine the area, we just consider a strip. It is a strip whose length or height is y and width is dx. Here dx means that it is a small negligible quantity in x. So now these two vertical lines are very much close, and y is the length of the strip. And now here the area of the strip is equal to area of the strip is given by y into dx. You know, here these two strips are very much close, so that almost these two lengths are same, and since it is dx, therefore the area bounded by these lines is almost nearer to y into d of x, y into dx. Therefore this is the area of the strip known as elementary area. And this strip is known as arbitrary strip, and this area of the strip is denoted by dA. Now if we consider a large number of strips in between x is equal to a and x is equal to b and find their areas, find the elementary areas that are formed between these two lines and add them. Now the sum of those elementary areas gives rise to area of the region bounded by the curve y is equal to f of x with x axis and x is equal to a, x is equal to b. And therefore the area of the region bounded by the curve y is equal to f of x with x axis and x is equal to a, x is equal to b is given by integral of dA under the limits a to b. So it is integral of dA under the limits a to b represents the area of the region, as well as it is the sum of the large number of strips that are defined between x is equal to a and x is equal to b. It is the sum of sum to infinity, that is integral a to b into integral a to b d of a, which is equals to integral a to b, but you know d of a is equal to y dx, that is equal to integral a to b, where y is equal to f of x into dx. So that you just integrate the given curve f of x with respect to dx under the limits a to b. That gives the area of the region bounded by the curve with x axis between the lines x is equal to a and x is equal to b. Suppose if we consider one more curve, x is equal to f of y. Let us take one curve, x is equal to f of y, and the area of the region bounded by the curve x is equal to f of y with y-axis between the lines y is equal to c and y is equal to d. Now in this case, the graph be like this. Now this is x-axis, it is y-axis and origin, and this is the curve x is equal to f of y. Now this is y is equal to c line which is parallel to x-axis, and this is y is equal to d line parallel to the y is equal to c line parallel to x-axis, and y is equal to d, it is also parallel to the x-axis. Now let us find the area of this curve with y-axis between the lines y is equal to c and y is equal to d. Now here also we can consider a small strip, an arbitrary strip whose length is x units and width is dy. Then the area of this elementary strip or elementary area dA is equal to x into dy. Now the large number of these elementary areas gives rise to area of the region bounded by this curve with y-axis. Therefore, finally the area is given by integral x dy under the limits c to d, that is equal to integral c to d x dy, where x is equal to f of y dy. Therefore, the area of the region bounded by the curve with respect to y-axis is integral c to d x dy or integral c to d fy dy, and the area of the region bounded by the curve with a x-axis between the limits x is equal to a and x is equal to b is given by integral a to b f of x dx. And next, let us find area of the curve y is equal to f of x with x-axis and between the lines x is equal to a and x is equal to b when the curve is below the x-axis. Now, as shown in diagram, so it is x-axis, y-axis, let it be origin. Suppose if the curve is like this, now this is the curve y is equal to f of x which is completely below the x-axis under the limits x is equal to a and x is equal to b. Now, how to find this area? Now, here also we can use the same formula. Now, in this also, in this case, we can determine the area of the region bounded by the curve y is equal to f of x and x-axis with x is equal to a and x is equal to b is given by integral a to b y dx or integral a to b f of x dx. But you know, since the graph is or the curve is below to the x-axis in between x is equal to a and x is equal to b, then the area will be negative. But you know, the area of any region is always positive. The area cannot be negative. But numerically it is positive. But you know, the graph is, since the graph is below the x-axis, so that we get the negative value. But area is always positive. Hence, we should consider the modulus sign, modulus for this area. Numerically, the area is common, same. So that consider the absolute value of this integral, that is modulus of integral a to b f of x dx. Now this is area of the region bounded by the curve when the graph is completely below the x-axis between x is equal to a and x is equal to b. Now, in another case, suppose the graph y is equal to, or the curve y is equal to f of x between x is equal to a and x is equal to b. Sum of the portion is above the x-axis and rest of the portion is below the x-axis. Then how to find its area? Now let us see. Suppose if the graph is like this. Now between x is equal to a and x is equal to b. Now this is the curve y is equal to f of x. Now what is the area of the region bounded by the curve y is equal to f of x with the x-axis between the limits x is equal to a and x is equal to b? Here you see, this is the area bounded by the curve with x-axis, and this is also the required area bounded by the curve with x-axis and between the lines x is equal to a and x is equal to b. But you know, sum of the portion is above the x-axis. Now this portion meets the x-axis at some point, let it be some c. Now this point of intersection with the x-axis is some c. So that between x is equal to a and x is equal to c, the graph is above the x-axis. Therefore, the area is equal to integral a to c f of x dx. Now between x is equal to a and x is equal to c, the graph is above the x-axis. Therefore, the area of the portion above the x-axis is given by integral a to c f of x dx, and the area below to the x-axis defined between c to b, that is integral c to b f of x dx. You know, suppose if the graph is below the x-axis, then we can get a negative value, negative integral, so that, but area is always positive, hence we have to take the modulus here and add these two. Therefore, the sum of these two areas gives the total area of the region bounded by the curve y is equal to f of x between x is equal to a and x is equal to b, like this. Now let us find areas of some standard curves. Here, let us find area enclosed by the circle x square plus y square is equal to a square. X square plus y square is equal to a square. It is a circle with the center 0, 0, radius a units. So that geometrically, so it is a circle whose center is at origin. Now this is origin 0, 0, and radius of the circle is a, so that it is a comma 0, and this point is 0 comma a, this one is minus a comma 0, and this point is 0 comma minus a. So it is a x-axis, a y-axis, origin. Okay, negative x-axis, negative y-axis. So it is the general, the graph of a circle whose center is at origin. Now we are going to find the area enclosed by the total circle. That means area of this portion and area of this portion and this one and this one. So that we have to determine the areas of the four portions and add. Well, when we add all these portions, we get the total area enclosed by the circle. You know, the circle is symmetric about the x-axis and y-axis. Now here, the circle is symmetric about the x-axis and y-axis, we know. So that the area, it makes the equal area with x-axis as well as with y-axis. So that the portion above the x-axis is same as to below the x-axis. and with respect to y-axis, now these two portions are same. So finally, these four portions give equal value, so that we just find only area of one portion and multiply with 4, then it gives rise to the total area. Therefore, area of the region is equal to, or area of the circle is equal to sum of all these portions, 4 portions, and since all these 4 portions are equal, we can write it as 4 times of the area of the region, 4 times of area of the region bounded by the curve y is equal to f of x with x-axis and x is equal to 0, x is equal to a. You see, it is x is equal to 0 and x is equal to a. Now this is the line. Actually, it is a tangent to the circle also. Now, the area enclosed between these two lines, x is equal to 0 and x is equal to a with the x-axis, is this part. Now, this is the portion. Now, we are going to find area of that portion. Now, this is equal to 4 times of integral 0 to a y dx. Right now, here the equation of the curve is given by x square plus y square is equal to a square. But we have to integrate y with respect x, so that you better to change this equation as in terms of y is equal to f of x. For that, y square is equal to a square minus x square and y is equal to root of a square minus x square. Therefore, 4 into integral 0 to a y dx, where y is equal to square root of a square minus x square into dx. And now integrate this quantity, this function root a square minus x square. Then after substitute the limits. Now you know it's a standard formula. The integral of square root of a square minus x square into dx is given by x by 2 into root of a square minus x square plus a square by 2 into sin inverse x by a. You know, this is the integration to this function root a square minus x square. Now, by this formula, the area is equal to 4 times of integral of root a square minus x square is equal to x by 2. It is 4 times of x by 2 into root of a square minus x square plus a square by 2 into sin inverse x by a under the limits 0 a. Now this is 4 into, first of all substitute the upper limit in place of x, that is a by 2 into root of a square minus a square, of course it is 0, plus a square by 2 into sin inverse a by a, which is equals to sin inverse 1, minus of, now substitution of lower limit. When we substitute x is equal to 0, this part becomes 0, minus, and substitute here a square by 2 into sin inverse 0. Sin inverse of 0 is nothing but 0, so that it is completely 0. Hence it is 4 into, and this part is also 0, a square by 2 into sin inverse 1 is equal to pi by 2. Now, so 2 into 2, 4 gets cancelled, it is pi a square. Therefore, the area enclosed by the circle x square plus y square is equal to a square is pi into a square.